everyone, we are Group 2 and our team consists of 4 members, Tai Chi, Ivy Ling Hong Hong, Lai Wen Ling, and Lim Xing. Today, we will present the concept of electromagnetism, magnetic force through electromagnetic suction. We will cover the introduction, background study of the experiment, material use, procedures, result and observation, discussion, and conclusion. Electromagnetism is the study of how electric current create magnetic fields. In our experiment, we use a simple DIY solenoid made from a plastic straw and copper wire to demonstrate how magnetic field can generate lifting force. Specifically, we focus on electromagnetic suction, where a steel needle is pulled and held inside the solenoid due to the magnetic field generated by the current.
For the background study of our experiment, we will start with electromagnetism, which describes the interaction between electric current and magnetic fields. This concept is fundamental to many devices around us. Two key laws form the basis of this interaction, which is Ampere's law and Lorentz force law. In our experiment, we focus on the electromagnetic suction effect, where a solenoid generates a magnetic field gradient. This gradient pulls a metal needle inward, demonstrating how magnetic fields interact with dipoles inside ferromagnetic materials. Next, we apply Ampere's law, which states that an electric current generates a magnetic field around it. The formula is as given. Around a straight wire, the magnetic field forms concentric circles following the right-hand thumb rule. In a solenoid, the field becomes stronger and more uniform inside the coil, making it perfect for suction-based effects like in our setup. Lastly, we have Lorentz force law, which explains how magnetic fields exert a force on moving charges or magnetic materials. The formula is as given. The formula means a charged particle or object moving in a magnetic field experiences a force perpendicular to both its velocity and the field direction. We use Fleming's left-hand rule to predict this direction. In our solenoid, the magnetic force pulls the metallic needle into the coil, demonstrating this law in action.
In our experiment, we use 6 main components to build a simple electromagnet. First, we use 1.5 meters of insulated copper wire, which was coiled to carry current and generate the magnetic field. Next, we use sandpaper to remove the oxidation from the ends of the wire, ensuring better conductivity. For the power source, we connected two 3.7-watt lithium-ion batteries in series, giving us a total 7.4 watts of DC. We then used a steel needle as a ferromagnetic object to test whether a magnetic field was present. Finally, the plastic straw serves as the non-magnetic core of our solenoid, making this setup an air-core electromagnet. All of these components work together to help us demonstrate the basic principle of magnetic field generation through electric current. To carry out the experiment, first, we tightly wrap insulated copper wire around a plastic straw, leaving a few centimeters of wire at both ends. Then, we use sandpaper to remove the oxidation from the ends of the wire. This exposes the copper core, ensuring proper electrical contact with the battery. Before powering the circuit, we inserted a steel needle into the straw and observed that there was no magnetic effect at this stage. Next, we connected the strip wire ends to two 3.7-watt lithium-ion batteries in the series, supplying a total of 7.4 watts. Finally, we reinserted the needle into the straw and observed whether a magnetic field was generated strong enough to attract the needle. We compare the needle's behavior in two different conditions. First, without any power connected, we inserted the steel needle into the straw. As expected, it simply fell due to gravity. This confirmed that no magnetic field was present. Next, we connected the coil to the 7.4-watt power supply using two 3.7-watt lithium-ion batteries. When we inserted the needle again, it was attracted and remained suspended inside the solenoid. This indicates that a magnetic field was successfully generated by the current carrying coil and that the field exerted a force strong enough to act on the needle. These observations support the theory of electromagnetism that current flowing through a coil produces a magnetic field.
Next, let us discuss how our simple solenoid experiment works. So when we connected the coil wire to the batteries, three key things will happen. So the first one is magnetic field correction. Based on the theory of Ampere's law, the current through the coil wire generated a magnetic field inside the straw. Therefore, the solenoid, which made by wrapping the copper wire into a coil, can amplify this effect, and this let the solenoid act like a bar magnet. Second, needle magnetization. So when the ferromagnetic object, such as the steel needle in our experiment, is placed inside the magnetic field created by the solenoid, it becomes magnetized and also creates a phenomenon which is north-south polarity in the needle. And lastly, electromagnetic suction effect. Based on Lorentz force law, the solenoid's magnetic field is then exerted a pulling force on the needle and pull the needle toward the stronger parts of the field, which is the center of the solenoid. So this strong attraction is enough to suspend the needle against gravity. And this is why the needle stays suspended until we disconnected the power. So this highlights that the electromagnetic suction, the lifting force on ferromagnetic objects via magnetic field gradients.
In conclusion, the experiment successfully demonstrated that a current carrying solenoid produced a magnetic field strong enough to attract and suspend a steel needle. It validated both Ampere's law, which explained how magnetic fields are generated, and the Lorentz force law, which explained how those fields act on a magnetic object. Overall, it is a simple but powerful way to visualize key electromagnetic principle, and it reflects the same concept used in real technology like magnetic levitation system. That's all. Thank you.